Welcome, my name is Matt, and for those of you that are familiar with the channel, what I've decided to do is sort of create a library of videos that are not so much repair and actual real-time diagnosis, but more videos that will give you a foundation and understanding of different performance control components. It's called the Understanding and Diagnosis series. All right, and welcome to a common fixture specifically for this series, but also in other videos, the Dry Erase Board of Knowledge. So one caveat for this one, I realize fully, of course, that a lot of people are going to be familiar with this material to some extent, and some people are going to be extremely familiar, and therefore they watch my videos with the express intent of looking for every mistake I make so that they can point it out to the public. But there will be many opportunities to do that in this video because there are many different types of fuel systems, and this will mostly be applying, of course, to fuel injection systems particularly. But there are many different types of systems. We're going to talk about a specific one, which will be the typical return system with a fuel pump feed to the rail and then controlling the pressure by a fuel pressure regulator with a vacuum control for the return back to the tank. So, and don't worry, if you don't know what that means, we're of course going to explain it, but we're only going to be talking about the typical return system. There are what are known as returnless systems, and there's even systems with electronic control of the fuel pressure, but this is going to be more for 90% of the people out there that are going to recognize this system on their cars. And actually, we're going to more focus on the fuel pressure regulator itself, which actually does apply still to those other systems to a point. The testing would often just be different. But let me go ahead and draw up a figure here on this system. And the beauty of this, the best part, is the whole theme with this channel is when you get an understanding of these parts, it eliminates a lot of the needs for you to use like troubleshooting guides and flow charts and stuff. You kind of figure it out yourself, and nowhere is this going to be more apparent than on a fuel pressure regulator. Once you understand mechanically how the regulator works, pretty much the rest of the video isn't even needed because you'll be able to figure it all out just using your brain. A case in point, very commonly people who diagnose a fuel pressure problem, they look in the flow guide and it tells them at some point remove the vacuum hose from the regulator, and then you look for a fuel pressure change. Is it supposed to increase or is it supposed to decrease? Well, you have to look up and remember. You won't have to do that, I promise. For the rest of your life, you will always know what happens when you remove the vacuum hose from a fuel pressure regulator and what you should expect. Not because you remembered the flashcards on remove hose and expect this result, but because you understand how the regulator works. So when the vacuum hose is removed, you will know what the mechanical effect will be. You know what the result would be on the fuel pressure, and you will never forget it for the rest of your life. So let's go ahead and understand the system, and then we're going to apply these concepts onto an actual car just to validate them and help them sink in. All right, so I've got a rough diagram here. As you hopefully realize, I am not an artist by any means. I am fully cognizant this looks like something from 5th grade sex education on the female reproductive system, but I will explain it, and I promise you it will make sense, and you will understand it for the rest of your life. But in blue, I've put for the fuel pressure regulator, the FPR, the functional active components that are important to understand. But basically, here's your fuel tank. You have your fuel pump, which of course drives up fuel to the fuel rail. You will have your injectors here, and of course the fuel goes through the injectors. The injectors deliver fuel into the intake manifold, and to be specific, there are newer designs where it's called direct injection, where the injectors deliver directly to the cylinder. We're not really going to cover that, but basically you'll get your, let's actually put fuel in green here so it stands out a little bit. Your injectors will deliver fuel. It's important to know that the delivery of fuel through the injectors is controlled not through fuel pressure so much, but through the length of time that the injectors are open. So it's very important to understand that as this fuel comes through, if more fuel is needed, the engine is under load. Most of you guys are familiar with the 14.7 to 1 stoichiometry. As more air enters the engine, more fuel would be needed to keep this ratio. That fuel delivery is controlled by keeping the injectors open longer or closing them and keeping them open for a shorter period of time. And it's known as duration or injector pulse. So you may have like 8 milliseconds that the injector is open under a full load and maybe a couple of milliseconds that the injectors are open under idle. So you can see how that would control the fuel delivery. Very important to keep this in mind and understand that. If the fuel pump is delivering fuel, and there's of course going to have to be some pressure here. And let's say the pressure is typical 55 psi. And that fuel runs out of the injectors. Hopefully you have enough of a conceptual idea of this that you would see that by opening the injectors longer, it would drop the fuel pressure in the rail because we have more fuel coming through the injectors here, which of course would be like releasing your thumb off the end of a hose and dropping this fuel pressure. So the thing is, we need a way to maintain that fuel pressure as constant regardless of the time the injectors are opening and closing. And that is the purpose with this fuel pressure regulator here. And the way it works is very, very simple. You can see that what we've got here in blue is a diaphragm, and the diaphragm is connected to a spring. And I know for those of you guys that are engineers or professional automotive technicians, you've probably been trained on this, and it's not exactly like this, I know, but the idea is to get the theory of understanding here. This is not an engineering class here. But the idea is, by default, the fuel pressure regulator diaphragm is going to want to be closed to greatly restrict the fuel flow. And the idea is, of course, this would create a higher pressure in the rail, and by default, that is where you would be at. Now, the thing is, if you think about it, you really don't need a really high pressure in the rail at idle. So why would it default to that position? Well, that's where this vacuum hose here comes in. What the vacuum hose does is it uses engine vacuum to counteract the spring. If there is a high vacuum in the hose, then you can see that it would pull up on this diaphragm, countering the spring, and therefore allowing more flow of the fuel to return to the tank. What effect would this have on the pressure? Well, of course, by opening this restriction, it would lower pressure to the rail. Now, the important thing to understand is that alone right there kind of tells you what you would do to diagnose this fuel pressure regulator. So before we explain how this works with the injector pulse length, let's think about this for a second. When is engine vacuum higher? Would that be at idle, or would that be when the engine is under load at wide open throttle? Hopefully you know, and if you don't, then sink it into your mind, that at engine idle, vacuum is going to be highest, okay? At engine load, when you open the throttle, you will reduce vacuum. So let's think about how that's going to work on our fuel pressure regulator, okay? At idle, we have high vacuum. So at idle, we're going to have a maximum return flow past the fuel pressure regulator into the return line. Also, at idle, there's going to be minimal injector pulse length. The idea is you need less pressure to maintain that flow at a minimal pulse length. If the pressure were very high, then what would happen is at that minimal pulse length, because the pressure is higher, you'd still get much more fuel delivery than desired. So we need to make sure that when we reduce that pulse length, we don't increase the pressure in the rail. the pressure in the rail would be maintained constant because when we reduce the pulse length, because of the higher vacuum, that reduction in flow is compensated for by the increased flow to the return tank, so we maintain that same pressure. Hopefully that makes sense to you and that's understandable. And by the way, do you see on this system is going to have two lines to the fuel rail, a feed line and a return line. Do you see that the return line on this system is going to be the one with the regulator on it? So if you need to identify the return line, which is going to be important in some diagnoses, and we'll get into that, it's important that you can differentiate which of those is the feed and which is the return by which one has the regulator on it. And also, real quick, off the point, but be advised that in a returnless system, this part here is actually going to be located generally in the fuel tank, so it kind of changes things dramatically, and you would only have one line to your fuel rail. So if you only see one line to your fuel rail, this isn't going to apply nearly as much, and the diagnosis is actually a lot more difficult if you have an issue. Now, let's get back to the original question from the start of the video. One of the things that they often have you do when you diagnose a pressure regulator, they want you to remove the vacuum hose and look at the effect that that would have on fuel pressure at idle. So, go ahead and answer that question without having to look it up in a flow chart or anything like that. Just use your brain. If we were to remove the vacuum line and this engine is at idle, and we are seeing 55 psi at idle, and we remove that vacuum line, what would the effect be? Hopefully you can see that if we remove this vacuum line, that is going to mean the spring is going to push this diaphragm down, restricting that flow, but because the pulse length of the injectors has not changed, this is going to have a fairly significant effect on our rail pressure. Now, so if the spring is working and the diaphragm is intact and everything, if we pull the vacuum hose, you can see how mechanically we would increase the pressure at idle. All right, let's do this. Let's go ahead and at idle, we reconnect the hose. What's that going to do to our diaphragm? When we reconnect the hose, it's going to suck up and counter the spring and pull that diaphragm back to its original condition, allowing that flow to increase through the return. And of course, we will go back to our usual PSI at idle. Okay, now, what is going to happen when we put this engine under load? Okay, so in other words, we step on the gas pedal and we're taking off from a stop sign or something. Well, pretty much, actually, the same thing is going to happen. When we step on the gas pedal, remember at idle we're at high vacuum, but under load we're at low vacuum. It's pretty much the same thing, except instead of disconnecting this hose, we're just going to basically greatly reduce the vacuum from the hose. The same effect is going to happen. It is going to remove the vacuum from that diaphragm. That diaphragm is going to restrict the flow, increasing pressure, but remember, at the same time, we are increasing flow through the injectors because of the greater pulse length, so we still will not get a significant change in the PSI, in the fuel rail. So hopefully that makes sense to you, and if it doesn't, then, well, I really don't know what to tell you, but maybe hang in because we're going to go ahead and apply this concept on an actual car, and we're going to see that these effects actually do take place as I've described, and maybe then it'll sink in. So let's go ahead and do that. So the first thing I'm going to do is hook up my fuel pressure gauge hose to the Schrader valve. This vehicle luckily does have a Schrader valve. I hate those demonic, sadistic engineers that do not put Schrader valves on cars. Why do they do that? You might as well put the diagnostic link for the scan tool inside the gas tank as far as I'm concerned. Notice I've got a shop rag here so I catch any spilt fuel. You always want to be really safe with that, especially on vehicles that don't have a Schrader valve where I have to rig some connection to tee into the fuel feed or something like that. That definitely can get a little messy. One of the best things to do actually is to just pull the fuel pump relay or something like that on the car to run it dry to relieve the fuel pressure. Typically what I do is I just depress the Schrader valve and just catch the fuel with a rag. That's just fine. But you want to make sure you're not around any open sources of flame and stuff like that if it's winter in your garage heater. But obviously we're doing fuel stuff here, so safety comes first. And what I've got here is my fuel pressure gauge, which I was able to conveniently locate right next to this fuel pressure regulator with, of course, the vacuum hose on it like we discussed. And what we are going to do is first, again, a safety thing. I'm going to just do a static fuel pressure test. This is for two reasons. First of all, it's a safety thing so I can make sure that I'm not getting a leakage at my gauge or at the connection at the Schrader valve or anything like that. And the second thing is that there's going to be some information we get from the static test. So to do the static test, all I'm going to do is just turn the car to on, but not start it. And that's going to go ahead and build up pressure from the fuel pump. So let's see what happens. And we can see that we are at about 45 psi. Now what I want to do is check really quick at my Schrader valve connection and make sure we're not leaking fuel. Obviously we're not because we're holding pressure, but I just want to be extra sure here. If we were dropping pressure here, that would be much more of a concern. And there's no fuel leaks or anything as far as my connections. So what I want to do is wait a couple minutes here and see if that holds. Okay, so after a few minutes, we can see that we are still holding very strong at that fuel pressure. What does this tell us? This tells us that we do not have anything like a leaking fuel injector, external fuel leak, or anything like that. It also tells us the fuel pressure regulator is probably also not leaking. It is also indicating that the fuel pump check valve, things like that, are not leaking. If we do see a drop here, then hang on, I'll tell you what you would do to diagnose what's wrong if you saw a drop at this point. But since we don't have a drop and we know that we're safe, I'm going to go ahead and start the car. Let's see what happens. Okay, so we've got the car started. We see the fuel pressure actually dropped a little bit to about 40. So one of the first things we want to do, does the fuel pressure drop when we add throttle? And we can see that it does not drop when we add throttle. If we had a P0171 or 0174 lean condition, or 0171 and 0174 on a V engine lean condition, and we saw a good drop, that would be almost certainly why we would have that check engine light code for the lean condition. Now, let's go ahead and what is going to happen when I remove the hose from my fuel pressure regulator? Well, we know what should happen. The regulator is actually open right now because of the engine vacuum through the hose. So we should see a pretty good increase in fuel pressure if I pull this off. And we see we do. It's back to almost the priming pressure. That's why the pressure dropped when we started the engine, because we added vacuum to it. So right now, we also, of course, have a vacuum leak here, so I'm just going to plug that with my thumb right now. But you can see that the increase in pressure is due to the fact that we've removed vacuum, which is the same thing that would happen, as I said, when you would apply throttle. Another good test that you can do is also the snap throttle test. Now think on a snap throttle, we're going to open wide open, removing vacuum from the fuel pressure regulator. That should cause a highest point on our fuel pressure gauge. But then, of course, on decel, that would be the highest possible engine vacuum you can get, which should actually lower the gauge just a little bit because of the additional vacuum further closing the regulator. So let's see what happens. And that's indeed what happens. It's going to go up and then down and stabilize back again at 40. So this indicates definite proper operation of our fuel pressure regulator, very much so with that test. And obviously, if you watch my channel, you've probably used a fuel pressure gauge before, maybe didn't know quite what to look at, possibly. But if you're not familiar with the fuel pressure gauge, there is a button here that you will press that releases the fuel pressure through this hose here so that you can safely remove your Schrader valve without fuel spraying everywhere. So make sure you do that. And finally, for those of you guys that are experts and you know about fuel trims, if you don't, then you can see my video, Secretive Engine Problem Diagnosis Fuel Trims, where it's really one of the most important diagnostic videos you'll ever watch. But we can see we've got really high fuel trims here right now. It's actually why this particular car is here, but it's a real simple thing that I cover in another video anyway. But what we're going to do is go ahead and take this hose off at idle. What is that going to do you think? Well, if you think about it, that is going to cause that fuel pressure regulator to close. The fuel pressure increases, but the engine is still at idle. With a higher fuel pressure, there will be more fuel injected per injector pulse. That would, of course, richen the mixture. So let's go ahead and see what happens. And our short term should start dropping pretty good now, and it is. And we should start seeing the long term follow suit before too long. See, we are definitely negative and dropping. Let's go over some of the common problems that you may have that may indicate a fuel pressure regulator and how you would go about testing them to make sure that you don't replace the fuel regulator if it is not the problem. So one common problem that would maybe key you towards the fuel pressure regulator would be if the engine is running rich. And there are a couple of codes that would be identified with this. You might even have a check engine light. I guess it would be a P072, maybe also a P073, I believe. But what are some reasons that you might have a rich condition, and what would be some ways to test it? By looking at our fuel pressure regulator here, can you think of maybe a very, very simple reason why you might have a rich condition? Just from your understanding of a fuel pressure regulator, what would maybe be the simplest thing possible? So obviously, a very simple reason you may have a rich condition is if there is a vacuum leak in your vacuum hose. If there is a hole in your vacuum hose where you no longer have the vacuum pulling up on this diaphragm, then of course you will have the diaphragm restricting, increasing your fuel pressure at the rail, and of course causing per pulse length more fuel to come in than would have been anticipated because you're now at a higher pressure in the rail. So every millisecond pulse length is going to deliver more fuel than if it was at the normal 55. Now, most of you guys who are experts in fuel trim and everything realize that that rich condition is going to be compensated for when detected by the O2 sensor, so the pulse length will be conformed so that we get a better air-fuel mix, and the short-term fuel trim will eventually level off. But the long-term fuel trim is still going to show that rich condition, and almost certainly you would throw a check engine light in this condition. So you would look and see that you have a vacuum leak in the hose as maybe one of your first steps. What's another way, very simple way that you could validate this as being the issue? Well, one of them is, does the engine only run rich at idle? Does it no longer run rich when it's under load? Because of course under load there wouldn't be vacuum here anyway. That would be even further evidence that you probably have a vacuum leak with that hose. Now, of course, another very valid test that you would do would be to take this hose off altogether and then directly apply vacuum. If directly applying vacuum to that regulator lifts up that diaphragm and we see the reduction in PSI, we know that that regulator works. We know there is not a problem with the regulator and that our issue is with this vacuum line to the regulator. Obviously, what you would do is at idle see if there is vacuum at this line. If there is not, you would correct the problem accordingly. But do you see how the understanding of the mechanics of the regulator makes it very easy to diagnose and test it and not replace the regulator if it's not necessary to do so? Now, another problem that you may have is when you continually have a lean condition. and you do your fuel pressure test and you determine that you have low fuel pressure. Now, obviously, the first instinct most people are going to have when they find they have low fuel pressure, probably 70% of people are just going to go ahead and replace the pump thinking the pump is bad. Do you see where you could have an issue where you would have low fuel pressure as a result of a faulty fuel pressure regulator? And do you also see where you may have other explanations for fuel pressure too? Somewhere along here is going to be a fuel filter. What if the fuel filter is clogged? What if there is some type of restriction in the fuel lines? It could also be the fuel pump itself is bad, of course. But another possibility could be, what if this spring is broken? Or what if the diaphragm has a leak? Either of those situations would cause this fuel flow to the return to always be very high. So in other words, the fuel pump is perfectly fine. There is no issue with the fuel delivery. The problem is the restriction to build the pressure is the fault. How would we be able to test that? Very easy test that you can do. Just simply pinch off this return line. And if you pinch off the return line and you find that your fuel pressure gets up to normal, then you know that you have a problem with the fuel pressure regulator at that point, and it would almost certainly have to be replaced. Keep in mind, sometimes in some cars, especially like the GM cars with the 4.3 liter Vortex, this fuel pressure regulator is actually located in the intake manifold itself, and it will leak fuel externally. So this also will cause a rich condition and low fuel pressure because the leakage is internal, and the internal leakage is of course going to cause a lot of vapor, causing that rich condition, decreasing of course the fuel trim into the negative. So this is a really good way that you would be able to test that, and you wouldn't even need the engine running. Just go ahead and plug up your return line with some vice grips or something like that. I use a special pair of hose clamps. Make sure you only do this on a rubber portion of the line, by the way. Increase your fuel pressure and see if it's maintained. If the fuel pressure drops, then you have either a leak in your fuel pressure regulator, or it also could be a leak in the fuel injectors, or of course it also could be a leak anywhere along this line. Now, of course, the way to test that would be very simple. If you also pinch off the feed line, so if you block off both ends of this and you continue to drop your static fuel pressure with the engine off, then you know that you either have leakage in the injectors, leakage with the line somewhere here, or in the case of an internal regulator, you may have an internal regulator leak. Make sure, of course, again, that if you do this, that you're blocking off only on a rubber component. Don't block off, obviously, a metal line or something like that. All right, and one other thing to keep in mind that will also help you with your fuel pressure regulator diagnosis, and that is, at least every time that I've seen it, if you have a rich condition in the vehicle and you find that when you apply vacuum to your fuel pressure regulator, you do not get any response, then almost certainly what's happened is this diaphragm has become compromised. And very often what you will find is that a lot of the fuel flow will actually go into the fuel pressure regulator itself, and as a matter of fact, into the vacuum line itself. Do you see how this condition, incidentally, would definitely cause a rich condition because the vacuum is still working at idle and you're actually drawing fuel through the vacuum line. So if you have that condition, very often what will happen is as you're doing your Mighty Vac pump, or if maybe you're like me, once in a while you actually suck on the tube to see if you can move the fuel pressure regulator. If you draw up fuel into that vacuum line, there's no reason that that should ever happen. The only reason that that would happen is you have a compromised diaphragm in your regulator and you will need to replace it. Almost certainly you don't need to do any further diagnosis. The fuel pressure regulator is compromised. You may have other problems too, but you also have a bad fuel pressure regulator in that event. All right, that is it. Short and sweet on this one, but the main thing is, if you understand just the functional components in a fuel pressure regulator, then you can see how really everything else I explained in the video becomes self-evident because you can simply put it together using your brain, knowing the mechanics of a fuel pressure regulator. So maybe go ahead and experiment on your own car, or the next time that you get a condition where you suspect a regulator problem, you will know several ways now to diagnose it and be able to make sure that you make the correct diagnosis and replace only what needs replacing. Thanks very much. I hope you found this helpful.